Hi and welcome to the first episode in our exploration of quantum computing and quantum programming. So let's get straight into it. The platform we're going to use to explore this is a platform called Jupyter and Jupyter Lab. If you're not familiar with that, I would definitely advise checking it out. But this is a general workbench for lots of areas that's used heavily by computer scientists, machine learning engineers. It's not specific to quantum computing, but it's a great way to explore new computing paradigms. Okay, so in this first episode, we're going to explore what is quantum computing. So if we kind of rewind the clock a little bit and we start to think about, the origins of computing as we understand it, you may have seen things like the difference engine before, and you can see this in the diagram on screen. And this is essentially computing using classical mechanics, using essentially representing numbers through the physical state of something such as an angle of a cog or some other physical thing. And then using classical mechanics of forces to turn gears and ultimately to perform computation. So there we're using the natural laws of physics, albeit the physical laws of mechanics to perform computation. Then if we jump forward to computing with electromagnetism, essentially this is the era we're in now, where we're using things like semiconductors and technology such as transistors to allow us to represent numbers as electrical signals and to represent computation as the changes in those signals. The diagram here is one you may recognize. It's a silicon wafer. So using those kind of ideas where we started with physical forces, then electromagnetic forces to perform computation, essentially quantum computing is allowing us to use the forces of quantum mechanics or the principles of quantum mechanics to perform computation. And this is essentially the logical extension of everything that we've done in computation up till now. So here we want to represent numbers through the quantum state of subatomic particles, such as a photon or electron. And then we want to use the natural laws of quantum mechanics to control and alter the state of the quantum state of those particles. And that ultimately is what allows us to perform computation. In quantum computing, we rely on three kind of core properties of quantum mechanics, this idea of superposition, entanglement, and interference. If you're not familiar with those, don't worry about them, but there is plenty of material online for anyone who wants to go deeper. The image that I'm showing here on screen is an image of a quantum computer, and this is one where you may have seen this or something like it if you've done any exploration into quantum computing. But actually what you see here is most of the apparatus on the top is related to cooling the device. Quantum computers typically need to run at temperatures close to absolute zero. And so the actual quantum chip, the quantum processing unit, is right down the bottom. I know the image is a little bit dark, but it's right down the bottom of this image. But the rest of the apparatus is cooling and controlling mechanisms. The last thing I want to talk about here is, in this introduction, is this idea of what are two different kind of core architectures in quantum computing. One is what's called gate-based or universal quantum computers, and the other type are what are known as quantum annealing computers. The gate-based are universal in the sense that they can perform any computation that we can consider, and essentially anything that can be done through a classical computer and potentially others. Quantum annealing devices are ones very specialized at solving optimization problems. They're not general purpose computers in that sense. But for the purpose of this series of videos, we're going to be using a quantum annealing device to work with and to use it to solve our problem. The last point then is why do we care about quantum computing? And we'll see this more in our final episode. But really it is the idea that quantum computers provide us the potential to solve very computationally challenging problems in a much more efficient way than we can solve with classical computers. And what we mean by classical computers really is standard computers that we're all familiar with, CPUs and GPUs. And quantum computers give us that potential to solve a range of problems much more efficiently than we can do with existing technology. And that's why we're all very excited about the potential of quantum computing now and into the future. So that's it for the first episode. Hope you found that a good introduction to quantum computing. Please join me in the next episode where I'll introduce the logic puzzle that we're going to use to build our demo that we're going to solve on our quantum annealing device. So I look forward to you joining me in the next episode. Thank you.